Hi. In this video, we will talk about Osprey optimization, which is the addition to the Firehawk optimization. So in one of the previous video, we have already discussed how Firehawk works. So initially, we have to start with some random weight. So we are taking some n number of weights, each of d dimension, and we have to then find out the best value for that. So based on the Firehawk hunting behavior, we have optimizing it. So this is the random initialization of each weight vector of d dimension, and such n vectors we are creating. And after that, we are finding the fitness value. So fitness value is nothing but the error made by the model. So we are dividing this data set into our data set into train and test part. We are training the model, we are testing it, and we are calculating that what is the error. So based on the minimum error or the maximum accuracy, we will divide this random weights into hawks and preys. So those solutions or those weight vectors which will generate minimum error, those n number of weight vectors, we will treat it as a firehawk. So out of this capital N, some small n, we will treat it as a firehawk, and remaining m we will use as a prey. So normally number of firehawks are quite less than compared to preys, and that thing is simulated here into the diagram as well. After that, we have to calculate the distance of each firehawk from the preys. So this is the formula. We are finding the Euclidean distance of lth firehawk from kth prey. So L vary from 1 to n because we know that there are n firehawks. So this is the schematic diagram of that lth distance between lth firehawk and first prey, distance between lth firehawk and second prey, and so on. So for all this, we have to calculate the distance. And then we have to update the position of the firehawk, because firehawk will move depending upon to the situation. So FL new, that is the new position of the lth firehawk, is given by the position of old firehawk plus R1 into GB. GB is the global based firehawk, right? The one which is having the minimum error in the prediction, that is considered as a global based. And R1 and R2 are random variables between 0 and 1. And FH near is the nearest alternate firehawk. So using this formula, we will update the current position of the lth firehawk. This is the simulation. And then we are also updating the prey position, because when firehawk drop the sticks, the preys will move around. So the new position of qth prey is given by its old position plus R3 into FHL. So R3 and R4 are the random variable again. FHL is the lth firehawk position, and SPL is the safe distance from that firehawk. So if it is very close to the firehawk, then distance is not safe. So SPL is considered as a safe distance. So SPL is nothing but it's an average of all the preys, because whenever there is a safe place, all preys will move together. They will come under that place. So we are taking the average of that position. And prey will also might move in the territory of other firehawk. That could happen. Fine, because when prey will move to save itself from the current firehawk, then it might enter into the territory of alternative or the side by firehawk. So position in that case, it is given by this equation, that old position plus R5 and R6 are some random variable. This is the alternate firehawk with respect to which we are calculating its distance, and the SP. So that is the safe place outside the lth firehawk, because now it is moving outside the territory of lth firehawk. And this is the simulation. Then we have a calculation of SPL and SP. So SPL is the average of all R firehawk in the territory of lth firehawk, and SP is the average of all possible firehawk preys. That is the M preys we have. Fine. So this is how we are iterating it through n number of times, and we are getting the good weight. But see what happens in optimization problem. There is always a chance of getting stuck into local optima or local minima. So we are trying to find out the weight which minimize the cost function. Our cost function is the error. So x is the weight vector, and fx is the cost for that particular x. That means the cost or the error into the prediction. So now assume that we are somewhere here. We have started with this random weight. We don't know what optimal weight is. So we have started with the random one. And using the firehawk, if we come to know that if we move in right direction, then there are chance that error will increase. So Firehawk will move in a particular way so that weight will be decreasing and somewhere it will settle. Because after reaching to this point, okay, so this is our weight. If we move in right direction or left direction, the error or the cost of the function will increase. So algorithm will understood that this point is the best point. That is the minimum error point. So algorithm will hold here. But see, this is not a global minimum. This is a local minimum. Actual global minimum value of weight is somewhere here. But we are stuck into the valley. So if we move in either side, then algorithm will think that as a cost is increasing, I should stop. So it will return us this weight value instead of this. So that is known as a local minima problem, and that is very common in optimization problem. So to come out from this kind of local minima problem, now the another part is added at the end of Firehawk optimization, that is Osprey algorithm. That is the Osprey algorithm. So this is the procedure we have already understood for Firehawk, and now this is the flowchart for that. I will show you the Osprey algorithm, that how it works. Let me just find it out where I have written it. It is not in this. Yeah, it is in this algorithm file. Fine. So see what we are doing is Firehawk optimizer we have already learned. Oh, fine. So this is just a copy of the statements from slide. So this and this are identical, right? Because this is just a this one. This is a Firehawk optimizer. So in that case, we are calculating these values based on this equation. Now in enhanced Firehawk optimization, what we are doing is after computation of the optimal weight, okay, determine the global best, we are calling the Osprey algorithm. So from this command will go to this Osprey procedure. Now what we are doing is here, we compute the new position of the prey as per equation number 6. So now our equation number 6 is like this. So the new position of, so P2 indicates the now second phase, okay, that we are calculating that in second phase. So kxy comma P2 is equal to kxy. So this is the old position of prey is equal, so new position is equal to old position plus lower bound plus r into upper bound minus lower bound divided by t, where t is number of iterations, which goes from 1 to capital T. X is 1 to capital P, Y is 1 to Q. Fine. So this will be, what we are doing is we are simply taking the old position and we are adding some random number into this. See, this is totally random. Obviously, it is restricted by the lower bound and the upper bound value. So what happens right now, we may be somewhere here, but when we add some random number, our weight might jump somewhere here, okay, somewhere here. So now when we do the optimization, algorithm knows that I need to move in this direction because my cost function is reducing. So there are chances that we might end up with the best solution, or the vice versa can happen. Suppose we are here right now, and when we add some random number, so that can be positive, negative, anything, fine. So our weight might jump to this position as well. So in this case, our optimal weight will be somewhere here. But we are generating many different solutions. So it is possible that some weight might jump here, some might jump here, some might be somewhere here, some might be here. So at least one, we can hope that at least one weight vector will be such that it will be in anywhere in this region and it will lead to the global optimal position. Fine. So that is the basic concepts of this random number generation, that old position plus we are adding some random number. Definitely bounded by this LB and UB, upper bound and lower bound variable. Otherwise, the value can jump anywhere onto the x-axis. So we have to specify the bound. Okay, once we compute the KP XY P2, now we have to update or we have to clip the value. See, if this computed value is between the lower bound and upper bound, then we have to accept it as it is. If this computed value is less than lower bound, then we have to consider lower bound as our output. because we already have a bound fixed that the value of the position cannot be less than this and cannot be greater than this. So if it is less than certain value, then our output we have to treat it as a LBY. So we are clipping it from the left end. And if this computed value is greater than the upper bound, that means it is on right hand side of that axis, then we will fix it to UBY. So we are clipping it from left and right if it is less than lower bound or the greater than upper bound. Otherwise we will keep it as it is. And finally, which K we have to select, whether the original one or the new one. Okay, so here the terminology is just a different variable is used. Actually this is the preposition. So what we were calling it here PR, okay, preposition, the same is here K, but as a Osprey we are using the different convention. So now how we are updating the preposition, that we will consider Kx, that is the new position of xth K, xth pre, as a KXP2, that means the newly computed pre value, if the fitness value of newly computed position or weight is less than the fitness value of the old pre. Okay, so consider that Kx is the old position of the pre, KXYP2 or KXP2 is the new position of the pre. So new position we have computed, we have applied the bounding on that. Now we have to check whether the new position should be accepted or not. So we should only accept it if the fitness value of newly computed position is less than the fitness value of the old position. So Rx corresponds to fitness value of old position of xth pre, and Rxp2 is the fitness position or fitness value of the newly computed position of the xth pre. So if it is so, we are updating Kx to the KXP2. Otherwise, we will continue with the Kx. It means if after this exploitation phase, if there is no update in update in the fitness value, or if fitness value is getting worse than the actual one, then we will continue with the original solution. But if we see some better value in that, then only we will update to that. And this procedure we will be repeating. So let's move to the code and we'll try to understand it now. See, in my first video, I have explained the code up to this part, and then I got busy in work and I could not record it. So now I will start it from here. So up to this we have done. So I advise or I insist that please you go and watch that video in detail so that you understand what exactly happening everywhere here is. Next is while FES less than max FES, that means we are iterating our algorithm some n number of generations. So this is just a number of iterations we are going through our algorithm. Iteration count is equal to iteration count plus 1. So we are simply measuring the count. Now pop total underscore total is equal to empty. So we are initializing one variable to null. It does not contain any value. And then for I in range, length of pop new. Now length of pop new is 125 because pop new we have already computed here, and we have assumed that there are 125 pre's. Obviously it will be a random number, but we have simulated it for this number. So whatever number is generated here, the same will be the length of this pop new. Now what we are doing is PR is equal to pop new of I. So I is initially 0. Then it will be 1, 2, 3 up to 124. So total 125 times this loop will iterate. And we are fetching one by one pre from that. Pre of 0, pop new of 0, pop new of 1, pop new of 2. So every time PR will be the ith pre. So for initial pre, what we are doing is FHL is equal to FH underscore position of I comma. This code will fetch the position of Firehawk, ith Firehawk. Then we are computing SP underscore L is equal to NP dot min PR. So what we are doing is we are finding the safe position under the nth Firehawk. So we are basically running this equation. Okay? That is the simulation of this equation that we computing the mean. So you see this is actually a mean. Mean means average. Sum up all the values divided by total number of values. So that is the mean. So here we are computing the mean or the safe position under the nth Firehawk. Then we are generating two random numbers. IR is equal to np.random.uniform 0, 1, 2. So between 0 and 1, we are producing two random numbers. Now we are finding FH underscore near position. So FH near, if you remember, fine, somewhere here we will be using the alter, FH alter. So we have to find out the position of alternate Firehawk first. So that is given by the new position of Firehawk is equal to old position plus IR of 0. So we are fetching the first random number. IR is a list of two random number. So first random number into global based minus IR of 1. So second random number from this into FH near. Okay. Sorry, FH near we have computed here. So FH near is we have taken as a random Firehawk from the all the Firehawks, and then we are updating the position of Lth Firehawk in this way. So we have the formula for that here. FHL new. See, FHL new is equal to FHL, that is the old position of Lth Firehawk, plus some random number R1 into global based minus R2 into FH near. Now FH near, how we are computing? We are randomly picking up one of the Firehawk from all possible or the 12 Firehawk we had. If you remember, you see that we had 12 Firehawk. Again, it could be random because whenever we run it, the number of Firehawk will be decided based on the random number generated. So one time it may be 12, another time it may be 10, it may be 8, maybe 20, whatever. But right now it is 12. So out of 12 Firehawk, one of the Firehawk will be selected, and with respect to that, the position of Lth Firehawk will be determined. So FH underscore L new is equal to FH underscore L plus this is R1 into global based minus R2 into FH near. So we have simulated this equation, right? This one. This equation has been simulated. Next, FHL new is equal to np.clip FHL new varmin varmax. So we have to now clip this value. See, always we will make sure that value, computed value will not go outside the our upper bound and lower bound. So varmin and varmax are our upper bound and lower bound. So we are clipping the value of FHL new using these two variable. So varmin is having value minus 10, varmax has value plus 10. So if any value is less than minus 10, then it will become minus 10. If it is greater than plus 10, then it will be plus 10. And if it is in between minus and plus 10, then it will be preserved as it is. Right? So we have just clipped that value. Next, pop underscore total dot append FH underscore L underscore new. So see, initially this was empty. Now we are appending the newly generated Firehawk position into that. So one Firehawk we have added into this after updating its position. Now we have to update the praise position. So for Q in range PR dot shape of 0, we know that PR is a 125 dimensional vector now. So first PR we are fetching, and then again we are generating two random numbers, and we know that how to update the position of prey now. So position of prey is updated in this way: old position plus some random number into FHL minus R4, that is another random number, into SPL. So we already have calculated all those values. So let's now apply the equation that new position of PRQ is old position of PRQ plus random number R3 into FHL minus R4 into SPL. So that we have computed already, right? Again, we are clipping that value to make sure that it will not go beyond the our bound. Then pop dot tot dot append PRQ new. So whatever new position we have calculated, that we are appending to this one. Right? Then IR is equal to random number uniform. Again, we are generating two random number because now we have to calculate the other things. We have to calculate now FL alter, FH alter, because that will be used here. So we have to find out what is FH alter, and then we have to update the PR with respect to that. So two times PR will be updated here using this with respect to Lth Firehawk, and then with respect to the nearest Firehawk or the alternate Firehawk. So first we are calculating the alternate Firehawk. So we are generating random number and we are also fetching the FH alter randomly. Then we are applying the same formula that new position of Qth prey is equal to old position plus random number into FH alter minus random number into SP. So this equation now got simulated. See, FH alter we choose randomly, and then this equation has been fired, that old value of this plus random number into FH alter minus R6 into SP, right? So this has been computed here, and again then we are clipping that value and we are appending it to the pop underscore dot append. So this will be iterated for all praise, okay, for particular FH. Then now FH will change. Now it will be a second firehawk. The same the things will be iterated for the second firehawk as well. Then third firehawk and so on. It will go on and on. Fine. So this will give us the optimal weight. Fine. Until this condition loop will break, this will go on. And once we get the optimal weights in pop_torch, now we are applying the Osprey algorithm. So in a Osprey algorithm, now we will simulate the remaining equations. These equations we are going to execute this one. So see, if I greater than is equal to len of pop_torch, then continue. Fine, this is just a check. Otherwise what we do, we will fix lower bound and upper bound to var min, var max. Then random is equal to np.random var number. We have generated one random number. And then we are applying this equation. See, this is our equation. The updated value of prey is equal to old value plus lower bound plus r into upper bound minus lower bound divided by t. So that is what happening here. That a new value of prey is equal to old value in pop total I plus lower bound minus random number r into upper bound minus lower bound divided by iteration count plus 1. Okay, so t is a iteration actually, but why we are doing iteration count plus 1? Because t should start from 1. But in Python code, when we write a loop like this, I in range len pop_torch, I will start from 0. So division with 0 is not possible, so we are simply adding plus 1 to make it divisible. Fine, so that equation has been simulated. Then again we are clipping it. We are clipping that value. So ultimately this equation will be executed. That if value is less than lower bound, then keep it lower bound as it is. If it is greater than upper bound, then fix this updated value to upper bound. And if computed value is in between lower bound and upper bound, then consider that updated value. So that three equations will be simulated using this function, np.clip. So this is the inbuilt clip function of NumPy library. Then we are computing the cost function or the fitness value of this newly computed position. So we are calling cost function x comma y, and that cost function cost will be available here. Now we have to check whether this newly computed cost, okay, for see this is the old position of prey and this is updated position. That means this is the old weight and this is updated weight. Now we have to check if this cost function, cost for the new position, that is fit underscore new underscore p1, if it is less than the cost of this weight, then we have to accept the newly computed position. Otherwise we will continue with the old one. So that we are doing here. See, update the position if the new fitness is better. So ultimately what we are going to do is we are going to compute now, apply the equation number 8 now. That if the fitness value of newly computed position is less than Rx, it means it is better. Then consider the computed position, otherwise go with the older one. So that thing is happening here, that for j in range len of cost, for j length of cost, so we are iterating it, this loop we are iterating, and then we are checking that if j is less than length of cost, fine, that means if it within the bound, and then here what we are making the check is that if fitness of newly computed prey is less than the cost of jth prey, okay, cost of jth prey, then we have to update this pop total I by the x underscore new underscore p1. And we are also updating the cost of j by this newly computed cost. When it will be done? Only if it is less than the computed cost, okay, of the fitness value or the cost of the newly computed prey is less than the cost of old position or the old prey. Then we have to update the position and we have to update the corresponding cost. If this condition is not true, then nothing will fire. That means we will continue with the old data only. After doing this, we are so this is the identical again, what we have already seen, that we have to sort the cost based on index. Fine. Forget about this. This is just for a check. Then we are sorting the cost. We are sorting all the populations and we are finding the best weights. Fine. Best underscore weights is equal to this. And we are doing FES plus is equal to len of pop total. And this will continue until we have this loop is over, and finally it will return the best weights. So this is how we are combining this two stuff to overcome from the local minima. Fine. So when we are adding the random number, so as I said that there are chances that we can move in this direction or we can move in this direction. So when we move in this direction, cost will go up. So algorithm will not accept this position. It will continue with the original one. But if randomly it is jumping in this way, then cost will decrease. Gradually it will decrease and somewhere it will settle here. So there are high chance that we will get the weights which will minimize the cost function or which will minimize the error. So actually there is a combination of these two and that tends to give a better results. So that was all about Firehawk optimization and Osprey algorithm. That is what I could understand from the code and the reading and so on. So see, when you will see this video very first time, you will find it very confusing. You may not understand many things, but when you read it again and again, when you will go through this again and again, I assure that you will understand lots of things. Because when the same has happened to me. When I have checked the code first time, I did not get anything. Then I read the paper, I saw some video, then I again came back to the code. I repeatedly went through code and papers again and again, and I'm quite much clear that what exactly happening there. Fine, so many technical things are there which are still confusing. I have not included into that, but still we can explain that. Okay, what is happening? Fine, line by line, it may not be possible to explain that why this line or what that line is doing and so on, why these parameters and why this optimizer, but that's okay. They may not be interested in exact code. You can show them this flowchart and you can explain them that how it is working. This is the philosophy of this. Right? Hope that you will get it. Thank you.